Well, hi there, boys and girls. Today we're going to talk about the fundamental theorem of calculus, and it has two parts, and so today's video is only over part one. And this is probably my favorite discovery that Newton or Leibniz found. It's an amazing connection between a function and its antiderivative, or the area under a curve of a function, and what its antiderivative does. Now, we have been playing around with this Riemann sum stuff, and we have been trying to do things like the limit as n approaches infinity. We want to put an infinite number of rectangles, and we want to add them up with this summation. And so we've got this infinite product. I've got function heights and then times a width. And we said yesterday in our video that we now are going to call this the integral from a to b of f of x dx. Now, what Newton actually did is he took this summation and he stretched it out. So if you stretch this e out, that's where this little symbol came from. That is a stretched out summation. S for summation, it stands for this infinite summation. The delta x, the width of each rectangle, went to 0, and through what's called the limiting process becomes dx. So this is still a product. So when you are doing an integral, you are doing a product. And so what we're going to say today is that it is equal to the antiderivative, or any antiderivative of f, evaluated from b to a. This is a y-coordinate, and we are going to subtract these y-coordinates. So both of these are y-coordinates. So this is saying that if you want to find the area under a curve, or we said yesterday the net signed area, then it is exactly equal to any antiderivatives change in their y-coordinates between a and b. This is an incredible connection that's going to allow us to find area under any curve very, very easily. This is pretty amazing. Now, this second part we're not going to worry about today. That's FTC number 2, and that says a lot of other things. Right now we're going to talk about net signed area under a curve, and I'm going to show you several examples of that. But for now, we are going to say that capital F is any antiderivative of f. So it can be any plus c that you want. Let's go take a look at what I'm saying. This is a picture of y equals 2x, and I've got it on the interval from, let's look at from 0 to 1. So like 0 is your a and 1 is your b. And so what if we wanted to find the area under the curve down to the x-axis from 0 to 1? This would be pretty easy to calculate. This is just the area of a triangle. This point right here for 2x is the point 1, 2. And so it has a height of 2 and a base of 1. And so this area is base times height divided by 2. This area is 1. Now let's take a look at the antiderivative of 2x. This happens to be x squared plus 0. So this is like capital F. It's an antiderivative. Now, what the fundamental theorem of calculus says is that the integral, or the area under the curve, or net signed area under the curve, of 2x from 0 to 1 dx is equal to the antiderivative change in y-coordinate. So I'm going to denote this by x squared as my antiderivative, and I'm going to put these little brackets here, and I'm going to put the b down, the a down there and the b up here. This is going to indicate I want to plug in 1 and I want to plug in 0 and subtract them. Why are we subtracting? Because we're trying to find the change in the y-coordinate. In other words, how much does x squared's y value change from 0 to 1? Well, at 0 it's 0, and at 1 it's up here at 1. What is this change? This change is up 1. You can even see from the table, from 0 to 1, the y-coordinate went up 1. The connection is the change in this y-coordinate is exactly equal to the area under the curve of its derivative. That's pretty neat. Let's take a look at another example. Oh, that's an old picture of x squared. Here I have y equals cosine x, and I want to look at the interval from pi over 2 out to pi. And I want to find the net signed area under the curve from pi over 2 out to pi. But this time I want to do it with cosine x. So I want to find out how much area is under this curve, but it's net signed area. The way we talked about yesterday, this has to be a negative value because all of this is under the x-axis. So it's not really area this time, it's signed area. So this is going to be as something negative. It's got to be less than 0. Alright, so what we're going to do is we can go find any antiderivative for cosine. Can you think of a function whose derivative is cosine? Well, of course you can. It's sine of x. And so what we want to do is we're going to find how much sine of x, how much its y-coordinate changes from pi over 2 to pi. So I want to find the sine of pi, and then I'm going to subtract the sine of pi over 2. This is the fundamental theorem of calculus. So this area is how much the y-coordinate changes. Now let's take a look at graphically. At pi over 2, we know the y-coordinate of the antiderivative is up here at 1. And at pi, we know the y-coordinate is 0. How much did this y-coordinate change? Well, it actually decreased by 1. It went down 1. And you can tell from pi over 2 to pi, these are just the decimal equivalencies. From pi over 2 to pi, the y-coordinate decreased by 1. So the answer to this is negative 1. Does that mean it's negative 1 area? No, it means the has an area of 1, but the negative denotes that the area is all underneath the x-axis. Okay, so let's do some other examples here. Which function is an antiderivative of the function shown? So this is f of x. What we want to find is which one of these is capital F of x. Are any of these antiderivatives of this? Well, this graph is pretty easy to see. This has a negative slope. It has a negative slope of down 2 over 1. It goes through the origin, so this is clearly y equals negative 2x. Which one of these functions is the antiderivative of this? Or in other words, if I take capital F and I take the derivative, I need to get negative 2x. So you can go through here and tell this derivative would be negative 2. That derivative is 2x minus 4. Here it is right here. Negative x squared plus 4, which would be right here, negative x squared plus 4, is the antiderivative of negative 2x. So we would call that capital F of x. All right, let's do it. What is a possible value of the integral of 2 sine of 2x dx? Now this would mean I have what's called an indefinite integral here. So I need like some function that has a derivative of this. So again, I'm going to go through here and I'm trying to find capital F of x. So we can just go through here and take derivatives. The derivative of negative sine of 2x is negative 2 cosine of 2x. So it's not that. The derivative of negative cosine of 2x is positive 2 sine of 2x, because the derivative of negative cosine is, well, the derivative of cosine is negative sine, and then the negatives cancel each other. And we know this is like plus some c. And then the derivative of cosine of 2x is negative sine of 2x times 2. And the derivative here, of course, doesn't match this. So we have found our answer is B. This is the antiderivative for 2 sine of 2x. Or an antiderivative. Okay, which region represents the definite integral of f of x from 2 to 4? This means the area under the curve down to the x-axis. Is it A? No, it's not A, because that's to the left. B, this is above the curve. We don't want that. D is to the right. C is the region. All of this area right here. And we could even count it. 1, 2, probably 3, maybe 4. I mean, you can count boxes to figure that out. But the question is just which one of these is the region. And it's right there. All right, what is the value of the integral from 1 to 5 of little g of x dx? Well, this means from the fundamental theorem of calculus, the antiderivative of little g is capital G, original OG. That's right, I said it. All right, and so this is my notation for that, and this is going to be capital G of 5 minus capital G of 1, the change in the y-coordinate of the antiderivative. And so that's going to be right here at D. Okay, now we're going to learn how to actually type this in on the calculator. So I've got this function 0.2 x minus 2 times 3 plus 2. And so, no, I'm not going to do this one on the calculator. We're going to count boxes here. I'll show you on the calculator in just a minute. Anyway, the antiderivative of little h would be capital H, and we want to find the interval from 1 to 4. So we want to find the change in the antiderivative from 1 to 4. Now I have two of these that say that. I've got this, and I have this. Which one of these would be the correct answer? Well, we can just count boxes. This is a width of 1 and a height of 1, so here's one area. Here's another, so there's 3. There's 4 plus a little bit more. There's 5. There's 6, but that probably makes up for what I added here. And this is probably almost another whole one. Well, it's got to be b. 1, 2, 3, 4, 5, 6, and about 0.75. So you just count. You can count boxes if you want. Here I've got a table of values. What's the antiderivative of little f? Well, it's capital F of x. And I want to evaluate this from 1 to 4, which means I plug in 4, and I plug in 1, and I subtract these. So the way we answer this is we can come to the table. Capital F of 4 was 3.6. Capital F of 1 is 1, so this answer is 2.6. So what is the area of the shaded region? Well, this means we want to find the antiderivative between a and b, and that is f of b, capital F of b, minus capital F of a, right here. Can't see that enough. All right, now we're going to actually find a value. Here we're going to use our calculator. Now we can do this by hand. We can find any antiderivative of 2x, which is x squared, and we can evaluate it from 1 to 5, which means you plug in the top number and then you plug in the bottom number and you subtract them. The change in the y-coordinate of x squared is 24 from 1 to 5. That thing goes up 24 units. That means the area under the curve from 1 to 5 of 2x is 24. Let's see how to do this on the calculator. From the home screen, you can hit F3, or you can hit second 7. You can see right there, there's the squiggly little s. F3, go down to integrate, and the parameters are, or the buttons are, function that you want to integrate. Sorry, try that again. I want to integrate 2x. So function you want to integrate, comma x, comma lower bound, comma upper bound, close parentheses. Enter, the answer is 24. You can also do this from the home screen. You can type in the original function 2x. Now let me change my window, so I've got a pretty good window here. Negative, let's go from -2 out to at least 8. And I need to see y minimum -1 up to about, let's see, up to, oh, I don't know, let's see, up to 20. I probably don't need to see that high, but anyway. So let's graph it. So here's the picture of 2x, and we want to find the integral from 1 to 5. So from the graph screen, you can hit F5 for your math menu. F5, scroll down to integral, and lower limit is 1, and the upper limit is 5. And this area is 24. Okay, so let's do one more by hand. The value of the integral from 2 to 4, 3x squared, the very first thing you do is go find any antiderivative. Now I'm going to be silly here. I'm going to find x cubed plus 1. There's an antiderivative for 3x squared. I didn't need the plus 1, but I want to show you that it doesn't matter which antiderivative you find. And you find the y-coordinates change between 2 and 4. So I'm going to plug in a 4. 4 cubed is 64, plus 1 is 65. 2 cubed is 8, plus 1 is 9. 65 minus 9 is 56. But what if I'd have just used regular old x cubed from 2 to 4? 4 cubed is 64, 2 cubed is 8, and I still get 56. So you can grab any antiderivative that you want. Okay, well that is it, and I will see you guys tomorrow.